Correlation simply means that there's a relationship between the two variables, which allows us to predict what will happen to one variable by knowing the level of a second variable. So, using the example above, the correlation between ice cream sales and crime rates means that if we observe a high crime rate, we can predict that ice cream sales will also be high. If ice cream sales are low, we can predict that crime rates will be low. So, it allows us to make that kind of prediction. And that's what makes it important and makes it powerful. So, correlation simply measures the direction and the strength of the relationship between two variables. Some of the statistics that we have talked about so far couldn't talk about strength, and some of them couldn't talk about direction. Correlation could not tell you direction. I'm sorry, chi-square couldn't tell you direction, but correlation can do that. We had ones that would measure strength of the relationship that we talked about last week, and others that didn't do that. So, correlation allows us to talk both about strength and direction, not about causal relationships, but about strength and the direction of the relationship. It also can't tell us which variable is independent and which one is dependent. So, that is what we do as researchers when we are setting up our hypotheses, and we have to have a reason to believe that one of those is independent and one of those is dependent. Correlation doesn't point us there statistically. That has to come from our understanding of what's logical in terms of the relationship between two variables. So, if we talk about ice cream sales and temperature, which is the example that was in a few slides ago, we certainly wouldn't believe that the temperature is controlled by how much ice cream is being sold, meaning that ice cream sales are the independent variable and temperature is the dependent variable, right? We wouldn't argue that if we all go buy a whole lot of ice cream from the grocery store, the temperature is going to go up because that is the independent variable, the one that's causing a change in the other one. It makes a whole lot more sense to say that temperature controls or has an impact as an independent variable on ice cream sales, and that the warmer it is, the more ice cream people are going to want to buy, and the colder it is, the less ice cream someone's going to want to buy. So, correlation cannot tell us which variable is independent and which one is dependent. We have to do that as researchers, as scholars. We have to have an understanding of what those associations or relationships might be like. There are some cases where we really can't tell which one is the cause and which one is the effect. One example is crime rates and the number of streetlights. So, this was an example that had been used for quite a while to talk about how if we want to reduce crime, we need to deal with the broken windows problem, was one of the ways that it was put by city planners and administrators and analysts. That if we make the community, the sidewalks, the streets look better and we make them brighter and cleaner, people will care more about their community and there'll be less crime. And on one hand, that makes sense. But it also makes sense that when you have a neighborhood that is brighter and cleaner, that it's probably brighter and cleaner for reasons other than that, and that may be contributing to the lower crime rate. So if you have a street that has 6 streetlights on it, it's a pretty brightly lit street. People are not going to commit crime on that street because they're going to be seen, possibly. But also possible is that that street may be a wealthier street where less crime is likely to happen on the street corner, as opposed to a street that may only have a light at each end, and there's a lot of darkness along the street at night. Why is there darkness on the street? The community may not have enough money to put more street lights in, and a lower income community is probably going to have a higher crime rate, and just adding more streetlights on that block may have very little effect on crime because there are so many other factors to take into account. So usually we have a sense of which one is the independent and which one is the dependent variable, and we want to test with that idea that we want to know what is causing something else. But we can't always know which one is independent and which one's dependent, and correlation can't help us here. Correlation takes the scatter plot of data, and this connects correlation to regression, which we'll talk about next week, because correlation doesn't always give you this line. But I want you to be thinking about the logic of correlation and regression together. So I'm going to go ahead and talk about this notion of the best fit line. So correlation takes the scatter plot of data and fits a mathematical best line through the data, one that represents what is happening in the relationship. We looked at the scatter plots before and we kind of saw a trend going up or going down in the data that led us to think that there was a relationship. Most of the people who went to the library frequently didn't watch as much television, and people who rarely or never went to the library tended to watch more television. So that gives us a sense of a trend line within the data. So that's a line that runs through the scatter plot. And it's more than just kind of eyeballing it. It is actually a mathematical line that is created that along the path within the data that minimizes the total sum of case deviations from that line. Now, if you remember deviations from, we talked about that when we were doing a number of different statistics, right? When we talked about standard deviation, we were talking about distance from the mean. We talked about z-scores, and it's a standardized unit of distance from the mean. So we're coming back to some of that logic, and we can do that because we have interval ratio level data, and we can calculate the mean, so we can measure distance between a point and that mean in the way that we did in some of our earlier calculations. So just keep that notion in the back of your head, because when we get to the calculation part, it's going to look very familiar. It's going to look like some things that we've already done. So here's a very simple scatter plot with just a handful of pieces of data on it. And this is the percent of respondents who approve of late-term abortion. And that's abortion that happens. I think that the legal definition would be after the first trimester, but it may be in the third trimester of pregnancy. So we can see the general trend appears to be that between 1995, which is this first data point, and 2004, which is this last, or 2003, excuse me, which is this last data point, that although there's some up and down, the general trend is that approval of late-term abortion has been declining. Okay, so we would probably draw a line in this data that, would kind of, if we were to draw what the curve looked like, we'd sort of connect them all and we'd see that up and down. But what the logic of correlation, the logic of this best fit line is that it's going to draw a line that's going to minimize the number of differences between. I'm wondering if I can. Pointer does not help me. I apologize for this. It's I'm new to using this software, and the pointer isn't going to really help me, but we'll see. So if I were to draw a line through the data that takes us there, so maybe this is what that line would look like. And so it's about fitting a mean line. So we're going to be able to measure the distance between wherever this point is on the line and this score. And then the distance between this point and this score, and this point and this score, and this point and this score. And we want to mathematically find the best line, the one where if we take all of those distances and we add them together, that it's the smallest number possible. Okay, that is the smallest number possible. So it minimizes those deviations between the line and each point on the scatter plot. Correlation compares the relationship between two variables, and both variables must be interval ratio level in order to perform correlation. Now, sometimes we take ordinal level data, particularly if we have Likert scale data, something like strongly agree to strongly disagree, or we have a range of possible ordinal responses. Typically, we have to have more than 5. Different books will tell you different things. But if you have 7 or 9 or 11 points on your scale, and it's an ordinal level scale, then often we will treat that data as though it is interval ratio. Whenever we do that, whenever we violate one of those requirements, we have to be very careful about how we interpret the data, because we're going to get a numeric response back when the response options were not numeric to begin with. So we have to be really careful. Remember the issue that we had when we were calculating the median For ordinal level data, it's like, well, what did that tell us? It's the middle category, but it gave us a number. So we had to remember that 1 meant this, and 2 meant that, and 3 meant this. And so that median is giving us a number that tells us about what that category response was and what that was labeled, not necessarily what, an actual number. So the 2 didn't make any sense. Okay, you probably remember doing that very early in the semester. So correlation and regression are based on a mean line. So it's that hypothetical line that is the best fit through a scatter plot. And this line will have that minimum level of deviation between the line and each point on the scatter plot. So this is kind of giving you an idea of what that mean line looks like. So each dot represents a respondent, and the mean line minimizes the distance between each data point and that line. And we can also, within this, there's an even spread above and below the line. So you're going to have, it's the mean line. And what did the mean tell us? Half the scores above and half the scores below. So this notion of a mean line through the data is a line where half of the deviations are above and half of the deviations are below.